Hello, this is Module 4.2, the continuation of MOSFET Fundamentals. So for this module, we will cover the regions of operation of a MOSFET, the basic IV curves, and channel length modulation. So from the first module, we learned that there is a quantity defined as the threshold voltage that defines when the transistor is conducting from source to drain. So that means the first region of operation is defined to be when the gate source voltage of the MOSFET is less than the expected threshold voltage. So if this is true, the transistor is off and there is no current flowing through the transistor. So we call this the cutoff region. So here. And then the next region of operation is when the transistor is on, so VGS is greater than the threshold voltage, but the VDS, the drain source voltage, is between 0 to VGS minus VTHN. So from the first module, we remember that VGS minus VTHN is defined to be VDSAT, so the saturation voltage. So from the PMOS, everything is reversed, because if you remember that the PMOS requires the negative voltage, so it will only become positive if the terminals are reversed. So this is this region. If these conditions are true, this region is called the linear or the triad region. So the transistor is on and it acts as a resistor. So it's an approximate linear curve to be like a resistor. So the current for a linear region transistor is defined to be this. For an NMOS is defined to be this for a PMOS. So for context, this is called the process transconductance of the NMOS, and this is the process transconductance of the PMOS. So the process conductance is usually defined by the oxide width, the mobility, and the ratio of the width and length of the transistor. So the next region is the saturation region. So this region occurs if the transistor is on and the value of VDS is greater than VDSAT. So this is when the channel pinches off in the drain side, and current here is constant. So constant, it means that it is independent of the value of VDS. So from the discussion of the regions of operation of a MOS transistor, so we can show the IV curves of these transistors and show the different regions there. So this one shows the ideal NMOS transistor IV curve. And then, so if you remember, if VGS is less than VTH, the transistor is in cutoff, and we expect that there is no current whatsoever for any value of VDS. And if we increase the value of VGS and we increase it to VTHN, the current also increases for increasing VGS. So as you can see here, you can see that VDSAT is approximately equal to VGS minus VTH, which is shown here. So if we increase the value of VGS, we expect that VDSAT also increases linearly. So the thing here is, for it only applies, so this assumption mostly applies if the value of VGS is high. It's relatively high. So at very low values of VGS, we expect that this assumption will not be valid. So from this boundary, we can see that the linear region is on the left side. So because VDS is less than VDSAT, which is here. So in the linear region, as you can see, IDS is approximately linearly dependent on VDS. So this is an approximate. So as you can see, so as VDS increases, IDS also increases. And then, on the right side of this boundary, where VDS is greater than VDSAT, we expect that the transistor operates in the saturation region. And from the equations earlier, you can see that the value of the drain current, or IDS, is approximately constant, or is constant, shown here. This slide shows the ideal PMOS transistor IV curve. So just like the NMOS IV curve, if VSG is less than VTH, it is in cutoff. So we have to take note that everything here is reversed. So instead of VGS, it's VSG. To know more about that, or if you forgot, you should look into Module 1 again. So that's why everything is negative here, shown here, VDS and IDS. So as we increase VSG, the transistor will turn on, and then as you can see, as you increase VSG, IDS, the magnitude of IDS increases. And now we can also show that there is a boundary here. So VDSAT of a PMOS is negative, so we use absolute value to make things simpler. Is approximately equal to VSG minus the threshold voltage of the PMOS. So as you can see, the same idea, just like earlier, the assumption will not be valid at very low values of VSG. That's why this approximation only usually applies when VSG is relatively high. So at the left of this boundary is the linear region. So as you can see, VDS and IDS are approximately linearly dependent on each other, approximately. And then at the right side of this boundary is the saturation region, which shows that the current is constant. So now, in this slide, I will discuss the non-ideal, one non-ideal effect of increasing VDS. So as you remember, if VDS is increased about VDSAT, the depletion region increases, right? But there is a phenomenon called channel length modulation, which if you increase VDS further, the depletion region increases also between the bulk and the drain, and there will come a time that the effective length, remember this is the length from source to drain, the effective length will be shorter. And from these assumptions, we can show that the effective IDSAT is now increasing because the length is going down. So this quantity is the process transconductance earlier, the Kn or the Kp. And as you can see, if the length is decreasing, this current increases. But if we want to model this, we use what we call a channel length modulation parameter here, which is this one, and it must be VDS, and it depends on the difference between the actual VDS and VDSAT. But remember that if we reach this level of channel length modulation, this quantity can be approximated to VDS because the saturation voltage VDSAT usually is very small. So therefore, if we use this idea and we model this idea, we must now include this quantity here. So instead of having a constant saturation current, it is now linearly dependent on VDS, and the slope of this is lambda, which is the channel length modulation. Okay? So how do we use these ideas, all these ideas? So I'm going to give an example. For example, this one. This is an NMOS. So given that VA is 1 volt, VB is 2 volts, and VC is 0.5 volts, Find the region of operation of the NMOS transistor if VTHN is 0.5. So, first step, you always find VGS and VDS. So VGS for this one is VB minus VC. So VB is 2 volts and VC is 0.5 volts. So you subtract that, you get 1.5. VDS is VA minus VC. And remember that VA is 1 volt, VC is 0.5, and then you subtract. And the next step, we have to approximate the value of VDSAT. So remember our assumption, it's approximately equal to VGS minus VTH. So VGS is 1.5, and then VTH is shown here to be 0.5. So VDSAT is 1 volt. So now, remember that using these VGS, VDS, and VDSAT, we can find the region of operation. And as you can see, it satisfies these requirements. So VGS is greater than VTHN. VGS is 1.5, VTH is 0.5. So this is true. And then VDS is between 0 and VGS minus VTH. VDS is 0.5 and VGS minus VTH is 1. So therefore, because it satisfies these requirements, the NMOS operates in the linear or the triad region. So another example, this is a PMOS. So given that Vx is 1.5, Vz is 0.7, and Vy is 1 volt, so find the region of operation of this PMOS transistor if the threshold voltage is negative 0.4. So again, we're just gonna do just like what we did in the NMOS, but remember, in a PMOS, the pertinent voltages are VSG and VSD because everything is reversed. So VSG is Vx minus Vz. So if we calculate that, Vx is 1.5, Vz is 0.7, therefore VSG is 0.8, and then find VSD. So Vs is Vx, Vd is Vy, so we subtract that. So Vx is 1.5 and Vy is 1, so that's 0.5. And then we find the saturation voltage, so that's VSD sat. So remember, the approximation is VSG minus the absolute value of VTHP. So VSG is 0.8 and VTH is 0.4, but the absolute value, that's positive, so we get 0.4. So now we have these quantities. Now we can find which region satisfies these voltages. So as you can see, VSG is greater than the threshold VTHP, therefore this is on, and VSD is greater than VSG minus VTH. So VSD is 0.5 and VSG minus VTHP is 0.4. Therefore, the region that has these requirements is the saturation region. Therefore, the PMOS operates in the saturation region. So in summary, this lecture converts the physics behavior of the MOSFET into its equivalent current and voltage equations. So this table shows everything that you need to know about the MOSFET. So in cutoff, when the MOSFET is in cutoff, the current is always 0. And in the linear triad region, remember that VDS or VSD is less than the saturation voltage, and they have these equations. And then when and as you can see, in the linear region, the current is dependent on the value of VDS or VSD for the PMOS. And then for saturation region, the voltage across VDS or VSD for the PMOS is greater than the saturation voltage. And if we are considering ideal NMOS or PMOS transistors, the current is constant. But if we consider channel length modulation, as you can see, we have a channel length modulation parameter. So thank you for listening.